In this video, we'll design a notification system that operates at production scale. Let's see what separates a production notification system from a smaller scale implementation. A prototype notification system can call an API like Firebase Cloud Messaging or SendGrid, pass a message payload, and successfully deliver notifications. For applications with modest user bases and predictable usage patterns, this approach works well and is perfectly appropriate. However, production systems operating at scale face fundamentally different constraints. Let's consider a food delivery application. Let's say it announces a flash sale for a popular restaurant. You need to notify all the users in the area, and if you send all notifications synchronously one after another, you will immediately run into problems. Firebase Cloud Messaging will start rejecting your request because you're exceeding the rate limits. Your message queues will back up, and by the time users actually receive the notification, the flash sale would have ended. A key consideration here is that provider rate limits often constrain us more than our own infrastructure does. Apple's APN service limits sustain higher volume sending, and Google's FCM has per project quotas. SendGrid has daily caps based on your plan level as well. Your architecture must account for these external limitations, not just your own server capacity. Beyond rate limits, production systems must coordinate delivery across multiple channels. Push notifications reach users who have the app installed. Email provides detailed content and permanent records. SMS reaches users without the internet access and commands high attention, but it does cost real money for every message sent. User preferences add another layer of complexity here. So some users would want to get notified by email only. Others would prefer push notification during work hours but not during evenings. Many may have quiet hours enabled during sleep. Regulations like GDPR in Europe and CAN spam in North America legally require honoring these choices. Cost management becomes essential at scale. SMS charges accumulate per message, and at high volumes, SMS costs can exceed your entire server infrastructure budget. A million SMS messages can cost up to $75,000 or more. So we'll look at specific numbers shortly. Now let's define our functional requirements. Now let's define what our notification system needs to accomplish. Multi-channel delivery forms the foundation. We need support for push notifications on mobile apps using Apple's APNs and Google's FCM. We need web push for browser notifications. We need email for longer content like order confirmations and newsletters. We need SMS for urgent messages like authentication codes. And we need in-app notifications for users actively engaged with their application. Each channel has a distinct characteristics worth understanding. Push notifications are essentially free per message and delivered pretty immediately, but users can disable permissions. Emails handle detailed content well and provide a permanent record, but deliverability depends on the sender's reputation. SMS costs money but reaches the users without an internet access and achieves near universal attention. User preference management gives recipients control over their notification experience, so users should be able to select preferred channels, opt out of specific notification categories, and configure Do Not Disturb work windows. Beyond being a good user experience, regulations actually like GDPR and CAN spam legally require honoring user preferences, and getting this wrong can result in significant financial penalties. Scheduled delivery enables the sending notifications at a specific future moments. A calendar app needs reminder 15 minutes before the meetings. A marketing campaign might need delivery at a specific hour. An important consideration here is that handling different user locations. A message intended for 9 a.m. should arrive at 9 a.m. in each user's local region, whether New York, London, or Singapore. We need proper handling of users' locations and local hours. Rendering engines like Handlebars or Jinja 2 handle variable substitution. A single notification like your order is ready for pickup should render appropriately as a brief push notification, a detailed email with order information, or a concise SMS message. We separate the content from the delivery logic. Delivery visibility completes our requirements. So, for example, did each notification reach its intended recipient? Did users open the messages? Did users click the links? Such data feeds the analytic dashboards and helps debug delivery issues and enables A/B experimentation. Now let's look at our non-functional requirements. Let's examine the non-functional requirements that shape our architecture. High throughput for burst handling is probably the most important characteristic of notification systems. Unlike regular web traffic which stays relatively steady, notifications are extremely bursty. When Spotify announces Wrapped feature is ready, when Amazon starts Prime Day, or when a news app breaks election results, you are suddenly going to be sending millions of notifications in seconds, not spread across 24 hours. Peak load might be 100x or even 1000x of your average load. Your system needs headroom for these bursts, which is why we use message queues like Kafka or RabbitMQ. The queue absorbs the burst while workers drain it at a sustainable pace. Latency requirements depend on notification priority. A two-factor authentication code must arrive within seconds because the user is waiting for at the login screen. If it arrives in 30 seconds, they'll request another code, get frustrated, and possibly abandon the login entirely. A weekly newsletter, on the other hand, can arrive any hour that day without anyone really noticing. So, we handle this with priority levels. High priority notifications like authentication codes skip the queue and process immediately. Low priority marketing notifications can be batched and delayed for efficiency. Reliability means we don't lose notifications, so once a system accepts a notification request, it must eventually attempt delivery. This requires durable storage before acknowledgement. If a server crashes mid-processing, we shouldn't lose the notifications it was handling. Kafka provides this durability by persisting messages. We aim for the at least once delivery, meaning we want occasionally sending duplicates, but we'll never silently drop messages. Scalability should be horizontal. If we need more capacity, we add more worker servers. No single component should bottleneck the whole system. Kafka partitions let us parallelize processing, so Kubernetes also lets us autoscale workers based on the queue depth. Cost efficiency matters more than you actually might expect. SMS costs roughly 1 to 5 seconds per message. Even free channels like push have infrastructure cost. Our architecture must enable smart channel selection, batching, and clear visibility into costs. Now let's put concrete numbers to these requirements. Let's do some math to understand what we're actually building for. Assume 100 million daily active users, similar to a large consumer app like Uber or DoorDash. Each user might receive an average of 5 notifications per day across all channels. That's 500 million notifications daily, roughly 6,000 per second at a steady state. If you have worked with web servers, 6,000 requests per second sounds very manageable. A single well-configured server can generally handle that load. But here's the critical point. Steady-state system doesn't exist in notification systems. A single event changes everything. When Spotify announces a Wrapped feature, when let's say Amazon starts the Prime Day, and when a news app breaks election results, you'll be suddenly sending millions of notifications in seconds rather than spread across 24 hours. Peak load might hit 1 million notifications per second, which is 150 times the average rate. So your system needs headroom for these bursts. This is why Kafka with sufficient partitions is very important. You can't handle a 150x spike with synchronous processing. Channel distribution shapes the infrastructure planning. So let's say 60% of notifications are push, 30% of them are email, 10% are in-app, and 1% are SMS. Each channel scales differently, so push flows through APNs and FCM, which impose their own rate limits. Email requires managing sender reputation with gradual IP warm-up. SMS costs money per message, so even 1% of 500 million requests is actually 5 million SMS daily at a significant cost. Provider rate limits constrain us more than our own infrastructure often does, so Apple's APNs will limit the sustained high volume without publishing specific numbers. FCM by Google has per project limits requiring quota increased requests for large applications. SendGrid for email has daily email caps based on your own plan. When planning capacity, you need to map out these external constraints carefully. Storage accumulates pretty quickly, so each notification needs metadata as well. For example, recipient, channel, content, status, and timestamps are main components of metadata. Let's call it 500 bytes per notification. At 500 million daily with 30-day retention, that's 7.5 terabytes of notification records. PostgreSQL with partitioning or Cassandra can handle this, but you need to plan your data life cycle pretty early in the process. Now let's examine the economics. Of running a notification system at scale because cost can surprise you. Push notifications are free per message from Apple and Google. APNs and FCM don't charge for delivery. However, you pay for the infrastructure to generate and send notifications. For example, worker servers, Kafka clusters, Redis for caching, and PostgreSQL for storing delivery status. At 300 million push notifications daily, you need substantial compute capacity. Estimate would be around $5,000 to $20,000 monthly in infrastructure spending on your cloud provider and how efficiently you have architected your system. Email costs depend on your provider and volume. So, for example, SendGrid charges roughly 10 cents per thousand emails on higher volume plans. AWS SES is similar at about 10 cents per thousand emails with no monthly minimums. And 150 million emails monthly, that's around $15,000 in delivery costs. But email has a hidden costs. Dedicated IP addresses run $20 to $80 monthly each, and you need several for reputation isolation. Email validation services like zero bounce charge per lookup to clean your list. Factor in the engineering effort for deliverability management as well. So budget around $20,000 to $30,000 monthly for a large-scale email operation. Now here's what the cost can escalate rapidly. SMS charges per message. So Twilio charges around $0.0075 per SMS segment in the US and more for international. A single SMS over 160 characters becomes multiple segments and each segment is billed separately. If one person of 500 million daily notifications are SMS, that's 5 million SMS daily or 150 million monthly. At dollar price point of 0.0075 each by Twilio, that's $1.1 million per month just for SMS. This is why smart channel selection matters enormously. You should use SMS only for truly urgent cases, for example, authentication codes, security alerts, and users who have explicitly requested SMS. Every architectural decision should be asking, can we avoid SMS or can we push first with SMS as a fallback? Infrastructure costs include Kafka clusters at roughly $3,000 to $10,000 monthly, PostgreSQL or managed database services, Redis clusters for caching, worker servers with auto-scaling and monitoring. For a system handling 500 million notifications daily, you should be estimating around $30,000 to $50,000 monthly in infrastructure. The key insight is that SMS dominate the cost at scale. You should be making cost optimization a feature, not an afterthought. Now let's look at the high-level architecture. Let's see how all these pieces fit together before diving into each component. The system begins with notification requests arriving through two paths. The first is the direct API calls where internal services call a notification API. Your payment service, for example, will call post/notifications saying send a receipt to user X. Your order service calls it when an order ships, and the calling service controls what exactly to send and what to send. The second path is the event consumption. We subscribe to Kafka topics and receive notifications automatically based on the business events. Let's say, for example, when a user sign-up event happens and it appears on the user's topic in Kafka, we automatically send a welcome email. The event producer doesn't even know about these notifications at all. This decoupling is very powerful for cross-cutting concerns. Both paths converge into our ingestion layer, which accepts the requests, validates the payloads, and writes durably to Kafka. We use Kafka because it provides durability through disk persistence and replication, handles massive throughput with horizontal partitioning, and supports multiple consumer groups for different processing needs. However, you can use any other Kafka alternatives by different cloud providers like Azure and AWS, and that would work as well. Now, here's the critical point. When we acknowledge a notification request, we guarantee its safety is stored in Kafka and it won't be lost even if our servers crash immediately after. The processing layer consists of worker services that consumes from Kafka. These workers handle the business logic, for example, resolving user preferences from Redis or PostgreSQL, checking opt-outs, applying frequency caps, rendering the content with Handlebars or Jinja 2, and determining which channels to use. This layer is horizontally scalable. More workers means more processing capacity. We can use Kubernetes here to, for example, autoscale based on our Kafka user consumer lag. Now, channel workers are specialized services for each delivery method. The push worker maintains connections to APNs and FCM. The email worker integrates with SendGrid or AWS SES and batches the requests for efficiency. The SMS worker communicates with Twilio. Each channel has different APIs, rate limits, and error handling, so separation makes operational sense. Data stores include PostgreSQL for user preferences, notification history, and content storage. Redis handles caching for hot data like user preferences and device tokens. Kafka serves as both the ingestion queue and the processing backbone. The key principle is decoupling through queues. Each layer scales independently if we do that. Now let's trace a single notification through this architecture. Now let's trace a single notification from request to delivery. This will help us understand what happens at each of these steps. The journey begins when a service calls our notification API. Maybe your order service, for example, calls post/notifications API endpoint with a payload specifying user ID, notification category, for example, our order underscore shipped, and variables like order ID and tracking number. Our API server validates the request immediately. Does this notification category exist in our registry? Is the payload schema correct? Are the required variables present? Validation catches errors early before we commit resources. If validation fails, we return a 400 HTTP bad request and the caller knows immediately about this. After the validation passes, we write to Kafka. This is a critical durability point. We use Kafka's acknowledge equal to all setting, meaning the message must be written to all in-sync replicas before we get confirmation. This adds maybe 5 to 10 milliseconds of latency, but it does guarantees the durability. Once Kafka acknowledges, we return to accepted HTTP to the caller with the notification ID for status queries. The notification is now safe. Even if our API server crashes immediately after, the notification will be processed. A processing worker picks up the message now from Kafka. The worker now fetches user preferences from Redis, falling back to the PostgreSQL on cache miss. Then it checks, has the user opted out for shipping notifications? What other channels do they prefer? Are they in quiet hours window based on their location? If the user has opted out, we mark the notification as skipped and then we move on. For eligible notifications, the worker renders content. If we fetch the content definition for this notification category, we substitute variables like order ID and tracking URL and generate the channel specific payloads. And push notifications, they get a short subject and body. Emails, however, they get full HTML with images. The same notification intent become multi-channel specific payloads. Finally, we route to channel workers by publishing messages to channel specific Kafka partitions, one for push worker and one for email worker. These specialized workers handle actual delivery to providers and update delivery status in PostgreSQL. Now let's examine how we divide responsibilities between different components. Let's discuss component ownership because clear boundaries make systems maintainable and enable independent scaling. The ingestion service owns the API gateway and initial Kafka partitions. It handles request validation, authentication, rate limiting at the API level, and ensuring notifications are durably stored. Its SLO focuses on API availability and latency. The notification API should respond within 100 milliseconds at P99 and be available at 99.99% of the time. That's 4 nines. So it doesn't care about delivery success, it's just that requests are accepted correctly and safely stored. The processing service owns core business logic workers, so it handles the preference resolution, content rendering, channel selection, and routing. Its SLO focuses on processing throughput and correctness. Notification should be processed within 5 seconds of ingestion and route to correct channels based on user preferences. It owns the preference system and rendering engine as well. The channel service owns the delivery to external providers. It maintains integrations with APNs, FCM, SendGrid, and Twilio. It handles the provider-specific rate limiting, error handling, retry logic, and device registration management. Its SLO focuses on delivery success rate. 99.9% of notifications routed to its workers should be successfully delivered to the providers. Provider-side failures like, for example, invalid email addresses do not count against it since that's outside its control. The platform services owns the shared infrastructure, Kafka clusters, PostgreSQL databases, Redis caches, Kubernetes clusters, and monitoring stack. It ensures that these systems are reliable, performant, and cost efficient. Other services are actually its customers. The analytics service owns the delivery tracking and reporting. It builds the dashboard showing delivery rates, open rates, click rates, and channel performance. It helps other services optimize their domain with data. This separation lets each service focus on its domain without stepping on other areas. Now let's examine multi-channel orchestration. Let's examine orchestrating delivery across multiple channels, which is where notification systems become interesting. When a notification request arrives, we rarely send through just one channel. Real-world scenarios requires coordinating between multiple channels based on user preferences, urgency, and fallback strategies. This orchestration layer decides which channel to use and in what order. Consider a food delivery app notifying a user that the order is ready for pickup. The ideal flow might look like, for example, send push notification first since it's free and immediate. If the user has push disabled or it hasn't opened the app in 30 days, suggesting stale device registration, then you will fall back to the SMS because that is time sensitive. Always send an email as a permanent record regardless of other channels. This kind of multi-channel logic lives in the router component. The channel router queries the user preferences from Redis, falling back to PostgreSQL if there is a cache miss. It checks several conditions. Has the user opted out of this notification category? Do they prefer specific channels? Are they currently in their quiet hours, let's say do not disturb window, based on their location? Or was there an engagement history with each channel? Based on these signals, it creates a delivery plan listing what channels and which channels to use. So channel priority varies by notification category. Authentication codes prioritize immediate delivery, which is push first, then SMS if push fails within 10 seconds. Marketing notifications prioritize cost efficiency, for example, email only, then maybe push notification and never SMS unless the user explicitly opted in. The routing rules are configurable per notification category. Fallback chains handle delivery failures gracefully. If push delivery fails because APNs return an invalid device registration error, we can automatically activate SMS as a backup for urgent notifications. This requires monitoring delivery status in near real time and having rules about when fallbacks activate. We typically wait 10 to 30 seconds for push confirmation before falling back, balancing urgency against unnecessary SMS costs. The fallback logic lives in a separate orchestration service watching delivery status updates. Now let's dive into the ingestion layer in detail. Now let's examine the ingestion layer, which is the front door to our notification system. The ingestion layer's job is straightforward: accept valid requests, reject the invalid ones, and durably store accepted requests for processing. Speed and reliability are paramount here. Every millisecond of latency in the API affects the caller's experience. API design should be clean and predictable. A typical endpoint looks like, for example, post/v1/notifications, accepting a JSON payload with a recipient user ID, notification category, channel preferences if overriding defaults, content variables, and optional scheduling parameters. Return a notification ID immediately so that the callers can check status later. Use the standard HTTP standard codes, for example, 202 accepted for successful ingestion since we are not delivering synchronously, 400 bad requests for validation failures, and 429 rate limiting for throttling. Validation happens synchronously before acknowledgement. Check that the notification category exists in our registry. Verify that the user ID format is valid, though we don't check if the user actually exists since that would add latency and coupling. Validate that the required content variables are present. Schema validation using JSON schema catches malformed requests early, and it's much better to reject clearly invalid requests than to accept them and have them fail later in the pipeline. Rate limiting at the ingestion protects the downstream systems. Use Redis with a sliding window algorithm. Apply limits per caller to prevent one misbehaving service from overwhelming the system. Also apply global limits to protect against coordinated spikes. When rate limited, return the HTTP 429 with the retry after header, indicating when the caller should retry. The critical step is writing to Kafka before acknowledging. We use the Kafka producer with x acknowledged equal to all, meaning the message must be returned to all in-sync replicas before we get confirmation. This adds maybe 5 to 10 seconds of the milliseconds of latency, but it guarantees the durability. Once the Kafka acknowledges, we return HTTP 202 to the caller. This notification is now safe. Now let's compare event-driven versus API-based approaches. Let's examine the two ways notifications can be initiated because understanding when to use each approach matters for system design. API-based notification is explicit. A service decides to send a notification and calls APIs directly. Your order service, let's say, calls a post/notifications when an order ships. Your payment service calls it when a payment fails. The calling service controls exactly when and what to send. This approach is straightforward and it gives the callers full control. Use it when the business logic for, let's say, should we notify lives in the calling service. Payment failure handling is complex with retry logic, so let the payment service decide when to notify. Event-driven notifications are implicit. Services publish their business events to Kafka without knowing or caring about the notifications. A user sign-up event appears on the users.created partition. A notification system subscribes to this partition and automatically sends a welcome email based on the configured rules. The event producer doesn't know about notifications at all. This decoupling is powerful for cross-cutting concerns. The rules engine determines which events produce which notifications. Configurations might say, for example, when event category is user.created, send notification category welcome underscore email to the user ID in the event payload. When event category is order.delivered, send delivery underscore complete. Rules can include conditions. For example, only send if the user's country is US, only send if the order's value exceeds $50. Store these rules in PostgreSQL or a configuration service with a UI for non-engineers to manage. Event-driven has advantages over the platform-wide notifications. So for example, imagine if you're adding a new weekly digest feature that summarizes activity across the entire platform. With API-based approach, you would need every service to integrate with your notification API. With event-driven, you subscribe to relevant events that already exist and send digests based on the accumulated activity. No changes would be needed from other services. The hybrid approach works best in practice. Use API-based for notifications tightly coupled to specific service logic. Use event-driven for notifications that react to business events across multiple services. Now let's examine message queue selection. Now let's examine choosing the right message queue, which is a foundational decision that affects everything downstream. Different queues have different strengths, and the choice affects system behavior significantly. Let me walk through the main options. Kafka excels at high volume and durability. It persists messages to disk, replicates across brokers, and handles millions of messages per second. Kafka retains the messages for a configurable period, often days or weeks, so consumers can replay from any point. This replay capability is incredibly valuable for recovery scenarios. If a worker had a bug that processed notifications incorrectly, you can fix the bug and replay from before the bug was deployed. Kafka's partitioning model lets you scale consumers horizontally by adding more workers. The downside is the operational complexity. Running Kafka well requires expertise, or you have to pay for managed services like Confluent Cloud or AWS MSK. RabbitMQ offers flexible routing with exchanges and queues. It supports complex routing patterns, which is to send a message to multiple queues based on routing keys, fan out to all consumers, or topic-based filtering. RabbitMQ prioritizes message acknowledgement and at least once delivery. It is simpler to operate than Kafka for moderate scale. The downside is throughput scaling. RabbitMQ struggles past hundreds of thousands of messages per second. For notification systems expecting millions per second at peak, RabbitMQ can become a bottleneck. AWS SQS is the simplest option. Fully managed, no servers to run, scales automatically, and extremely reliable. SQS works well for services without dedicated infrastructure expertise. The downsides are limited throughput compared to Kafka, higher latency, and no message ordering guarantees in standard queues. SQS first in first out queues offer ordering, but even with lower throughput limits. For most production notification systems, Kafka is the right choice. The throughput requirements and burst handling favor the Kafka's architecture. The replay capability is valuable for recovery. Yes, it's complex, but notification systems are actually complex. Accepting the operational cost, or you have to use a managed service, so feel free to choose any of these two options. My recommendation would be don't choose based on what's easiest in your current situation. You should be choosing based on what handles your peak load with more headroom and buffer. Now let's examine the priority queue architecture. Now let's examine the priority queues because not all notifications are equally urgent. An authentication code must arrive in seconds. The user is sitting at a login screen waiting for it. If the authentication code arrives in, let's say, 30 seconds, if it doesn't arrive, then they'll request another code, get confused when multiple arrive, and they might just give up entirely on the login. However, a weekly newsletter can wait hours without anyone noticing or caring about it. Priority queues let us handle both these appropriately without one blocking the other. You should be defining priority limits that match your business needs. A typical schema has 3 levels. P0 critical is for notifications that must arrive immediately. For example, authentication codes, security alerts, and similar urgent messages. P1 normal is for standard notifications like order confirmations, shipping updates, and password reset links. P2 low is for marketing and promotional content, for example, newsletters, recommendations, and re-engagement campaigns. You should be mapping each notification category to a priority level in your configuration. The simplest implementation uses separate Kafka partitions. For example, notifications-p0, notification-p1, and notification-p2. Dedicate workers to each of these partitions. P0 workers are always available and never shared with other priorities. P1 workers handle the normal load, and P2 workers can be scaled down during peak periods to free resources for other priorities. This isolation ensures the P0 notifications are not stuck behind a million P2 marketing emails. Worker allocation should also match priority SLOs. If your P0 SLO is delivered within 5 seconds, ensure enough P0 workers to drain the P0 queue faster than it fills. Monitor the queue depth by priority. Alert when the P0 queue depth exceeds the limits, like more than 100 messages waiting. Rate limiting by priority event prevents the lower priorities from consuming provider quotas. So, for example, if you have 1000 SMS per second capacity with a provider, you should be reserving 500 for P0, 300 for P1, and 200 for P2. If P2 exhausts its allocation, then it waits. P0 always has capacity available, and that is the goal. This approach prevents a marketing campaign from blocking authentication codes, which would be a serious incident. Now let's examine batch ingestion for marketing campaigns. Because marketing often needs to send notifications to millions of users at once. They don't want to make millions of individual API calls, they want to upload a list and let the system handle the distribution. The workflow starts with a file upload. Marketing prepares a CSV with user IDs and any personalization variables like first name or product recommendations. Then they upload it to S3 through an admin UI. The file might contain 10 million rows representing 10 million recipients. The UI shows upload progress and validates the file format before accepting it. A batch processor reads the file and creates individual notifications. This is a background job, not synchronous. It reads from S3, parses each row, validates the data, and publishes to Kafka. For 10 million rows, this might require 10 to 30 minutes depending on parallelization. The processor monitors the progress, allowing the marketing users to see completion percentage. Segmentation applies filters before sending. Maybe the campaign is intended only for users who made a purchase in the last 30 days or users in specific countries. Rather than having marketing filter the CSV themselves, the batch processor can apply segments dynamically. Query the user database for eligible users, filter the input list, and only queue the eligible recipients. Rate management spreads load across over many hours. Dumping 100 million notifications into Kafka at once creates a massive spike that can destabilize downstream systems. Instead, limit the batch processor to publish maybe 10,000 per second. The campaign requires longer to fully queue but doesn't overwhelm the entire infrastructure. Scheduling integrates with batch processing. Marketing often wants campaigns to go out at specific hours, for example, Tuesday at 10 p.m. EST. The batch processor can then accept a scheduled hour, prepare all notifications, but hold them until the delivery window. This is simpler than scheduling 10 million individual notifications. Progress visibility and cancellation are pretty important. You should be showing marketing how many notifications are queued, processing, delivered, and failed. Allow campaign cancellation if something is wrong. Now let's move into the processing pipeline. Let's examine the processing pipeline, which converts the raw notification requests into channel-specific delivery jobs. This is where the business logic lives: preferences, content rendering, and routing decisions. Kafka consumer groups provide a parallel processing, deploy multiple worker instances in the same consumer group. Kafka automatically distributes partitions among consumers. If you have 20 partitions and 10 workers, each worker handles 2 partitions. Add more workers to increase the throughput that you would need. Use Kubernetes horizontal pod scaler to scale workers based on consumer lag metric. When lag increases, meaning messages are piling up, Kubernetes adds more workers automatically. Each worker processes notifications through a pipeline of stages. First, fetch user preferences from Redis, falling back to PostgreSQL and cache mess. Check if the user has opted out of the notification category, if they are in the quiet hours, or if they have channel preferences that override the defaults. Cache preferences in Redis with a duration of 5 minutes since they don't change frequently. You can't query PostgreSQL for every notification at high throughput. Content rendering produces the channel-specific loads. Fetch the content definition for this notification category. Render it with the provided variables using Handlebars or Jinja2. Content for, let's say, order underscore shipped might have variables like push with the short subject and body, email with full HTML and tracking links, and SMS with a brief message. Render all applicable variants. Routing decides which channel to use based on the rules we have discussed earlier. Apply the routing rules for this notification category. Output is a list of channel-specific jobs. So each job goes to a channel-specific Kafka partition, push notifications, email notifications, and SMS notifications. Error handling determines what happens when the stages fail. If Redis is down, fall back to PostgreSQL. If content entering fails due to missing variables, log the error, mark the notifications as failed, and continue with the next one. Don't let one bad notification block the entire pipeline. Now let's examine deduplication. Because sending the same notification multiple times will annoy users and waste resources. Sources of duplicates are multiple. Network retries cause the same API call to be processed twice when the caller times out and retries, not knowing if the first request was succeeded. Kafka consumer rebalances can also cause messages to be reprocessed when partitions move between the workers. Event-driven approaches might fire multiple times for the same underlying event. Batch imports might accidentally include the same user twice. We need multiple deduplication layers to catch all these cases. So idempotency keys and ingestion handle the API retries. For example, callers include a unique key in the request header, often a UUID they generate. Before processing, we check Redis. Have we seen this key? If yes, return the previous result without re-executing. If no, we process normally and store the key with a 24-hour duration. This makes API calls idempotent. Calling twice with the same key produces the same result. Content hashing catches the semantic duplicates. Sometimes different requests represent the same logical notification. Hash the combination of user ID, notification category, and key content variables. Check if we have sent this exact notification recently. If we already sent, let's say, order shipped to user X for order 123 in the last hour, don't send it again. So you have to store the hashes in the Redis with appropriate durations based on the notification category. Deduplication windows vary by use case. Authentication codes might deduplicate within 30 seconds since users might click resend rapidly. Order confirmations might deduplicate within 1 hour since the order service might retry several times. Marketing campaigns might deduplicate within 24 hours to prevent multiple sends from overlapping campaigns. Configure the windows per notification category based on your business logic. Important thing to note is that deduplication is best effort, not guaranteed. In distributed systems, race conditions can still allow for occasional duplicates. If two workers process the same notification simultaneously before either stores the deduplication key, both might send. Except that some duplicates are possible and design your notifications to handle this gracefully. Now let's dive deeper into idempotency guarantees. Now let's examine idempotency, which means processing the same request multiple times produces the same results as processing it once. This property is essential for reliable distributed systems where retries are common. Why do retries happen so frequently? Network issues cause callers to retry, not knowing if the first request succeeded. Load balancers retry on failed health checks. Message queues redeliver when the consumers crash. Kubernetes restart crash pods, which then replaces the in-flight work. Without idempotency, each retry creates duplicates and inconsistent state. With idempotency, retries are safe. Idempotency keys are the standard pattern. Callers generate a unique key for each logical operation, usually a UUID. They include this key in the request header. Before processing, we check if we have seen this key. If yes, we return the restore result without re-executing. If no, we process the request, store the key with this result, and return. Redis is ideal for idempotency key storage. Use set next, which is set if not exist, with duration limit. This atomically checks and sets in one operation, preventing race conditions where multiple concurrent requests both conclude they are first. 24-hour duration is typical, matching the window where retries are likely. After 24 hours, we assume any duplicate would have been caught by any other means, or it doesn't matter anymore. Store enough information to return proper responses. Don't just store that you saw the key. You should be storing the result, the notification ID we created, the status we returned, any other information. When you detect a duplicate, return exactly what we returned before. The caller can't distinguish a cache response from a fresh one. Apply idempotency at multiple layers. The API layer handles the client retries with caller provided keys. The processing layer handles the Kafka redelivery with message delivered keys like the Kafka offset or a hash of the message content. Each layer protects against a specific retry scenario. Now let's examine the user preference resolution. Now let's examine resolving user preferences because every notification must respect what user has chosen. This requires efficient lookup of preference data for each notification, potentially millions of lookups per day. The preference data structure captures the user's choices. For each user, you should be storing a global opt-out flag if they have unsubscribed for everything, per notification category opt-outs, preferred channels with priority order, quiet hours, location, frequency caps, any channel-specific settings like different email address for notifications. You should be storing this in PostgreSQL as a JSON column or normalized relations depending on your query patterns. Caching is essential for performance. You simply cannot query PostgreSQL for every notification at 100,000 notifications per second. The database would not be able to handle the load. Cache preferences in Redis with user ID as a key. Set duration to 5 to 10 minutes since preferences change infrequently. On cache miss, fetch it from the PostgreSQL and populate the cache. Cache hit rates should exceed at least 95% for active users. Cache invalidation happens on preference updates. When a user changes their preferences in your settings UI, immediately delete or update their cache entry. You should be using Redis, del, or set with the new value. For distributed systems, publish a cache invalidation event to ensure all worker instances clear the stale data. Except that there is a brief window where the workers might still use stale preferences. This is usually fine since preference changes are rare. Preference hierarchy resolves conflicts. A user might have global preferences plus notification category specific overrides. For example, global setting is email only, but override for security alerts include the SMS. Resolution logic applies overrides on top of the global settings, define clear precedence rules, and document them for your organization. Default preferences handle the new users. Users who have not configured preferences need sensible defaults. Maybe default to push and email enabled and SMS disabled and no quiet hours. Store the defaults in the configuration rather than creating a database rows for every user. Now let's examine content rendering. Which produces the actual content users see. A rendering engine separates the notification content from delivery logic. Product managers can update messaging without code changes. The rendering engine converts the content definitions and variables into channel-specific work payloads. Content structures support multiple channels. A notification category, let's say order underscore shipped, has content for each channel, push with short subject and body, email with full HTML, SMS with a brief message. Store these as related records in the database. When rendering, you produce all the variants the user might receive based on the channel preferences. Rendering engines like Handlebars for JavaScript or Jinja 2 for Python handle variable substitution. Content might say, hi, username, your order, user ID, has shipped, details here, tracking URL. This engine substitutes the variables from the notification payload. Both are battle hardened and performant. Choose based on your organization's primary language. Conditionals enables the dynamic content. Content might need logic, let's say, show free shipping message if the order value exceeds $50. Otherwise, show standard shipping message. Handlebars support both if-else helpers. Jinja 2 supports full conditionals. Keep the content logic simple, however, because complex business logic belongs in the processing layer, not content definitions. Content should focus on presentation. Pre-compilation improves the performance significantly. Parsing content syntax on every render is expensive CPU work. Pre-compile the content definitions when they are created or updated, storing the compiled form. At render time, just execute the compiled definitions against the variables. Cache the compiled content in Redis or in process memory. Cache hit rate should be nearly 100% since content definitions change very rarely. Version control your content definitions for safety. Changes affect millions of notifications. Keep the versions. Allow rollback if new copy performs poorly or has errors. Handle the content definitions as code with review processes and approvals. Now let's examine the channel selection logic. Which determines which channels carry each notification. This logic balances user preferences, notification urgency, channel capabilities, and cost. Start with the notification category defaults. Each notification category has configured default channels. Password reset defaults to email because users expect to click a link. Flash sale announcements default to push notification because it's urgent and free. Authentication code defaults to SMS because it must reach users without app access. You should be storing defaults in configuration that non-engineers can modify. Apply the user preferences as overrides. If your defaults say push and email but the user disabled push, you should be only sending email. If the user opted out of marketing notifications entirely, you should be sending absolutely nothing. User preferences always win over system defaults. This respect for user choice is both ethical and legally required in many jurisdictions under GDPR and CAN spam. Consider the channel availability and freshness. We might want to send push, but do we have a valid choice device registration for this user? If they haven't opened the app in 90 days, the registration is like stale and APNs will reject it. Monitor the channel health per user, last successful delivery, registration freshness, bounce status for email. These are very important metrics to keep track of. You should be using this data to make smart channel decisions rather than wasting API calls on channels that are likely to fail for those users. Cost optimization influences the selection. SMS, they do cost money. Before choosing SMS, you should be asking, is this notification urgent enough to justify the cost? Is there a cheaper alternative that can still reach the user without me using the SMS? For non-urgent notifications, prefer push and email even if the user allows the SMS. Reserve SMS for emergency and cases where push and email fail. Build the fallback chains for reliability. Primary should be push. If the push fails or registration is stale, fall back to email. If the email bounces, escalate to SMS for critical notifications. Define these chains per notification category and priority. Now let's dive into push notification architecture. Now let's examine the push notification architecture, which reaches mobile and web users instantly without polling. Push is the workhorse channel for most consumer applications. It's free, immediate, and attention grabbing. But the architecture requires integrating with platform-specific services that each have their own protocols and quirks. APNs handles iOS and macOS devices. Apple Push Notification Service is the only way to send push notification to Apple devices. You cannot go around it. You connect using HTTP/2, authenticate with the JWT or certificates, and send notification payloads with device registrations. APNs is reliable but opaque. Success means Apple accepted it, not that the user saw it. FCM handles Android and web browser. Firebase Cloud Messaging is Google's push service. It also supports iOS if you want a unified API, though many organizations prefer direct APNs integration for better iOS reliability and features. FCM offers additional capabilities like topics for broadcast and message batching. Push workers maintain the persistent connections to these providers. Establishing connections to APNs and FCM has overhead, TCP handshake, encryption negotiation, authentication. Rather than connecting per notification, maintaining long-lived HTTP2 connections and reusing them. Use connection pooling libraries for it. You should be also monitoring connection health and reconnect automatically on failures. Payload construction differs by platform. APNs expect a specific JSON structure with an APS key containing alert, badge, and sound. FCM expects notification and data keys with their own formats. Construct the platform-specific payloads from your own in the generic notification content. Handle the payload size limits now as well. APNs allows the 4 kilobytes, FCM allows 4 kilobytes for most message formats. If your content is lengthy, compress or summarize. Don't let oversized payload cause silent failures. Response handling determines the behavior. APNs return HTTP status codes and error responses. For example, 410 gone means the device registration is invalid and should be removed from your database. 429 means slow down it that has been throttled. Map these to appropriate actions. Now let's dive deeper into APNs integration. Since Apple service has specific requirements that differ from other providers. Authentication uses either JWT or certificates. JWT is modern approach. Generate a short-lived signature with the APN's auth key included in the request headers. Signatures are valid for up to 60 minutes, so cache them and refresh before expiration. Certificate authentication requires provisioning and managing certificates that expire annually. JWT is simpler for most organizations. Store your auth key securely in AWS Secret Manager or similar. Never commit it to source control. Connection setup uses HTTP2 to api.push.apple.com for production or api.sandbox.push.apple.com for development. HTTP2 is required since Apple deprecated the old binary protocol years ago. Use an HTTP2 client library that supports connection multiplexing. Multiple concurrent requests over a single connection is what called connection multiplexing. This is the key for high volume. Libraries like APNs2 or for Go or Node APN for Node.js handle this well. Request structure includes the headers and the JSON body. Required headers are methods like post, path, 3 device followed by the device registration, authorization with your bearer signature, and APNs push type with your app bundle ID. The body is JSON containing the APS dictionary with alert content. Set APN priority to 10 for immediate delivery or 5 for power efficient delivery that might be delayed. Handle the response code appropriately. 200 means accepted, 400 means bad request, likely malformed payload. 403 means authentication failed. 410 means the device registration is no longer valid, so you should delete from a database immediately. For HTTP 429 means rate limited, so implement exponential backoff. Apple doesn't publish specific rate limits, but they will limit sustained high volume. Environment separation is also very critical. Development registrations only work against sandbox APNs. Production registrations only work against production APNs. Mixing them will cause failures, so note which environment each registration belongs to. Now let's examine the FCM integration. Now let's examine Firebase Cloud Messaging Integration, which is the primary way to reach Android users. Authentication uses a service account JSON file. Create a service account in Firebase console with cloud managing permissions. Download the JSON key file and use it to generate OAuth 2 access credentials. The Firebase admin SDK handles this automatically if you use it. Credentials expire after an hour, so refresh them before expiration. Store the service account JSON securely, not in the source control. The HTTP v1 API is a modern interface. Send the post request to the FCM endpoint with the project ID. The older legacy API still works but has duplicate features and worse error reporting. Use the HTTP one for newer integrations. Message formats are notification and data, and understanding the difference matters. Notification messages are handled by FCM on the device. FCM displays the notification automatically when the app is backgrounded. You specify subject and the body, and FCM renders it. Data messages are handled by your app code. FCM wakes up your app, which then decides what to do. For full control over notification appearance and behavior, use data messages with your own notification construction logic. Many apps use both: notification payload for when the app is backgrounded, data payload for foreground handling. Topic messaging enables the broadcast to groups without managing recipient lists. Subscribe devices to topic like news or sports. Sends to topic instead of the individual registrations. FCM handles the fan out to all subscribers. This simplifies sending to large audiences, useful for global announcements and app updates. Response handling maps to actions, so check results for per registration status. Error codes like invalid registration or not registered means the registration is bad, so remove it. Success doesn't mean the user saw it, only that the FCM accepted it. Now let's examine the device registration management. Let's examine device registration management because registrations are the addresses for push notifications. Managing them correctly is very important. Invalid registrations waste API calls and can damage your provider reputation if you send it to too many bad registrations. Registration acquisition happens on the device. Your mobile app requests permission to send notifications. If the user grants permission, the OS generates a device registration and passes it to your app. Your app then sends its registration to the backend for storage. This flow happens on the first launch and whenever the registration changes. Registrations can change after OS updates, app reinstalls, or device restores. Your app needs to check for registration changes regularly and report them. Storage schema links registrations to users and devices. A user might have multiple devices: iPhone, iPad, Android phone. Each device has its own registration, so store registrations in relation with the user ID, device ID, platform, registration value, created at, and updated at. Index by user ID for efficient lookup during notification sending. Handle the multiple registrations per user correctly. When sending a notification, fetch all valid registrations for the user. Send to each registration. If the user has 3 devices, send 3 push notifications. They'll see it on whichever device they are using. Don't deduplicate across the devices. Users expect to see notifications on all their devices. Registration refresh must be handled properly, so apps should check for registration changes on each launch and send updates to your backend. Your backend should upsert if the registration for this device ID already exists, update it. If it's new, insert. This handles both the initial and registration rotation. Implement an endpoint like post/user/id/devices that accepts the device ID, platform registration. Clean up the stale registrations proactively. When APNs return 410s for registration, delete it immediately. When FCM returns non-registered, delete it. Send to stale registration waste resources and can affect your provider relationship at high volumes. Now let's examine the registration refresh and clean up in more detail. Now let's examine keeping your registration database clean because registrations do go stale over time. Users uninstall apps, switch devices, restore from backups, or simply stop using the app. Active registration hygiene keeps your push infrastructure efficient and your provider relationships healthy. APNs feedback indicate invalid registrations through HTTP response codes. Status 4 times reason bad device token or unregistered means delete the registration immediately. You shouldn't be tried sending it to it because no one is actually be using it now. So log the removal for debugging, but acknowledge that automatically and remove it from a database. At scale, processing feedback correctly prevents wasting millions of API calls on dead registrations. FCM provides similar signals. Error code, for example, like invalid registration means the registration was never valid or became invalid. Not registered means the app was uninstalled. All these should result in immediate registration removal. This doesn't mean the user saw the notification, only that the provider accepted it. That's important to understand for your metrics. Proactive cleanup catches registrations that providers have not explicitly invalidated. Run the periodic jobs that identify likely stale registrations more than 90 days ago with no successful delivery in 30 days. Either remove them or mark them for reduced priority. Verify removal carefully though. False positives mean the real users stop receiving notifications. Registration versioning handles the edge cases. A user might reinstall the app, generating a new registration while the old one is still in your database. The new registrations will supersede the old one for that device. Use the device underscore ID to detect this. When a new registration arrives for an existing device underscore ID, replace the old registration. Keep only the most recent registration per device. Metrics help redefine your cleanup strategy. Monitor the registration success rate over time. Measure what percentage of sends succeed, fail with invalid registration, or fail for other reasons. High invalid registration rates suggest you need more aggressive cleanup. Low rates might mean you're being more overly conservative. Aim for less than 5% invalid registration rate on sends. Now let's examine push delivery optimization. Let's examine optimizing push delivery for high volume because naive implementations actually will hit provider rate limits and have poor performance. Connection pooling reduces the overhead significantly. Opening a new HTTP connection for each notification is expensive. There will be a TCP handshake, encryption notification, and negotiation, connection setup. At scale, all this overheads will actually add up pretty fast. Instead, you should be maintaining a pool of persistent connections to APNs and FCM. You should be reusing connections across notifications. HTTP2 multiplexing allows many concurrent requests over a single connection. For APNs, one connection can handle hundreds of concurrent requests efficiently. Batching group support does the notifications for efficiency. So FCM supports batch sending up to 500 messages in a single HTTP request. This reduces the HTTP overhead significantly. Group the notifications destined for FCM and send them in batch rather than one at a time. APNs does not support batching in the same way, but HTTP2 multiplexing achieves a similar efficiency by pipelining the requests. Payload optimization reduces the size. Keep push payload small. APNs allows a 4 kilobyte more. Smaller is better for network efficiency and processing speed. Don't include the data that app can fetch on its own. Instead of embedding the full order details, include just the order ID and let the app fetch details when the user opens the notification. Use short JSON keys. Compress where it makes sense. Parallel workers increase the throughput. Scale your push worker deployment horizontally. Each worker maintains his own connection pool. With 10 workers each handling 1,000 concurrent requests, you can send 10,000 notifications per second. Monitor the throughput and scale based on queue depth. Use Kubernetes autoscaling to add workers during the traffic spikes. Respect the provider rate limits to avoid being limited. APNs does not need to publish the specific limits, but they will limit sustained high volume. FCM documents the limits that vary by message format. Implement the client-side rate limiting as well. You should not be sending faster than the providers can accept. So use the bucket algorithms to smoothen out the traffic. Better to send steadily as 80% the capacity than burst and get limited. Now let's move to the email delivery architecture. Now let's examine the email delivery, which is the workhorse on notification systems. Email has universal reach, support rich content, and provides a permanent record. But email delivery is more complex than calling an API. Deliverability is a discipline unto itself. Email search service handles the heavy lifting here. For example, SendGrid, AWS SES, Mailgun, and Postmark specialize in email delivery. They manage the IP reputation, handle bounces, and provide analytics and ensure compliance with regulations. You should not be running your own SMTP servers unless you have deep email expertise and dedicated staff. The providers have entire engineering groups dedicated to deliverability that you cannot match, so please consider using cloud providers. Now, integration is used usually via API or SMTP. REST APIs are cleaner. Send a post request for recipient, subject, content, and metadata. SMMT, however, requires maintaining connections and speaking the protocol correctly. APIs are easier and what most organizations should use. SendGrid's API is well documented with SDKs for every major language. HTML email content requires careful construction. Email clients have wildly inconsistent rendering, so what works perfectly in Gmail might look broken in Outlook. Outlook uses a Microsoft's Word rendering engine for HTML, which is problematic as it sounds. Use HTML elements for layouts since CSS Grid and Flexbox have poor support. Inline CSS since it should be considered because since many clients strip the style definitions. Verify that across the clients using services like Litmus or email on asset before sending campaigns. Monitor important events using webhooks. Providers notify you when emails bounce, when recipients mark them as spam, or when users click links. Configure the webhook endpoints to receive these events. Process them to update the user records. Mark bounced addresses and invalid. Respect the unsubscribes and also monitor engagement for analytics. Ignoring these events hurt the delivery and violates the user expectations. Now let's discuss the sender reputation. Because it determines whether your email reaches inboxes or spam folders. Gmail, Microsoft, Yahoo, and other major email providers score senders based on their behavior. Send emails that people want to engage with, and your reputation will improve. And then send emails that get marked as spam. If you do that or bounce frequently, then your reputation will actually go down. And low reputation means your emails will go more often to spam, effectively be undelivered, so despite your technical success. IP warm-up is required for new sending IPs. If you suddenly send a million emails from a brand new IP address, spam filters assumes that you are a spam. That's exactly what spammers do. They spin up a new infrastructure and then they blast emails. You should be starting small. Send 100 emails the first day, 200 the second day, doubling gradually over 4 to 6 weeks until you reach the full volume. This builds reputation gradually. SendGrid, SES, and other providers offer warm-up guidance specific to their platforms. Dedicated IPs give you control and also more responsibility. On shared IPs, your reputation is pooled with other senders using that IP address. If they are reputable, you will benefit. If they are spammy, you will suffer. Dedicated IPs mean your reputation is entirely yours. If your email generates spam complaints, only you will suffer. But you will also only benefit fully from your good practices. Dedicated IPs make sense at volume of roughly 100,000 emails per month. Reputational signals include bounce rate, complaint rate, and engagement. Keep bounce rate under 2% by removing invalid addresses promptly. Keep spam complaint rate at under 0.1% by making a subscribe easy and honoring it immediately. High engagement with opens and click signals monitored is what actually makes your reputation better. While you do this, you should be always monitoring your reputation scores. Google Postmaster provide visibility into how Gmail views your domain. Microsoft SDNS, SNDS actually shows your Outlook perspective, and your email provider shows you aggregated metrics. Watch for sudden drops that might actually indicate a problem. Now let's examine measures that improve the email deliverability. These are standard requirements for production email systems. If you skip them, then it will actually result in a significant portion of emails going into spam. SPF, which stands for Sender Policy Framework, declares which servers can send email for your domain. You publish an SPF record and DNS listing for email providers' IP addresses. When receiving servers check the SPF, they verify that the sending IP is actually authorized for your domain. Fail SPF and you will look like a spammer or a phishing attempt. Work with the email provider to get the correct SPF record. It's a DNS record that looks like essentially what's shown on the screen, which is the F equal to SPF1, includes sendgrid.net, and then all. DKIM, which stands for Domain Keys Identified Mail, cryptographically signs your emails. You publish a public key in the DNS, and your email provider signs outgoing emails with the private key. Receiving servers verify the signature, proving the email was not modified in the process. And then the next thing is the DKIM is essential for deliverability. For example, all major providers support it. Set it up during the provider onboarding itself. DMARC connects the SPF and DKIM with the policy, so your DMARC record instructs receiving servers what to do with emails that fail authentication. For example, P equal to none means monitor only, P equal to quarantine means send to spam, and P equal to reject means block entirely. You should be starting with P equal to null while you get authentication working correctly, and then move to quarantine and eventually reject. DMARC also supports reports showing authentication failures, helping you detect spoofing attempts. Content best practices: improve the inbox placement, avoid spam trigger words and excessive punctuation, maintain a good ratio of content to images, include a plain version alongside the HTML, and make unsubscribe prominent and functional. These seem minor, but they accumulate in spam scoring algorithms.